Good morning and welcome to the morning session of day 2 of this wonderful conference. Without any further ado, Eduardo Martin Martinez is going to be measuring quantum fields.
All right. Thank you very much. Thank you very much to the organizers for inviting me here. There's Doreen, I see there, and everyone else. Let me begin with a little bit of a lot of acknowledgement. Near this university, we're in the traditional hunting grounds of the neutral and the Haudenosaunee, I don't know how to pronounce that. Haudenosaunee people? Haudenosaunee people, thank you very much. Just a little bit of the information of the indigenous peoples that were around this area. And in particular, if you want to read more about the treaties that govern this, that the relationship of the indigenous people and the British government and the Canadian government now. In this area, I invite you to, pointer, here, to check this website and check about the Longwood Treaty. And after this, let me tell you one thing. I'm a physicist, so I'm not a philosopher. I love philosophers, though, and in particular, I'm a fan of philosophers of physics. And I think we have a lot to learn from you people. And I hope, so I know that the talks here, I really like the format of these talks. Physics conferences, usually people interrupt all the time. And there's a lot, and facilitation yesterday was amazing. I think that's the style. I think like, raise your hand till I acknowledge you, and then that's not the way it works usually in physics, and I appreciated it so much. Let me tell you one thing, though, about my talk. I am very happy with interruptions. I kind of invite interruptions. If you don't feel comfortable with that, that's fine as well. But please, if there's something that I say that you disagree strongly with, which could happen, and I think it might happen, actually, very likely, please stop me and go for it. Have a go. I'm fine with that. I invite that. I'm here to learn as well. So that said, let's begin with the content. Right, so measurements in quantum theory. I mean, that alone is already an open problem, right? So what is a measurement in quantum theory? Well, the measurement problem is not a solved problem. Just forget about relativity in regular quantum theory. So here's a proposal. So measurements can give values, right? So people measure things, and, they may not have a definite value. They may have like an uncertainty interval or something like that. But it so happens sometimes we measure something, and we get a value. Like, is this thing here or not? Something binary, for example. Or you can say 42, whatever. You do some experiment, and the outcome is 42. And we can write those values on a notepad. Seems like a reasonable proposal, no? That thing, whatever your experiments are, sometimes they will produce data, and that data you can write down. In quantum mechanics, the traditional way in which we model that, so these things can happen, right? We make measurements and we get outcomes, is with the notion of idealized measurement. So what is an idealized measurement in quantum mechanics? Well, it's basically it's the fact, okay, fine, we use Born's rule-based reasoning to say, okay, with some probability we get this value, and if conditioned to obtaining this value, then we update our knowledge, or not going to get there. We update our state through a rank 1 projector on the spectrum of the measured observable. So you measure an observable, you get a 7, you update the state with the projector associated with the eigenspace of the eigenvalue 7 of that particular observable that you measured. So far, so good? Why? Oh, good. And then, but what about all the issues and nuances? Like, how do you go from a quantum state to a 42 on a notepad, and suddenly you update with a projector and everything works and seems to reproduce the experiment? What we call usually the quantum to classical transition. Where do you put the Heisenberg cut? When do you stop saying, okay, at what point it happens that you had a quantum state that was indeterminate, like probabilistically and by nature indeterminate, if you believe that's the way it goes, and suddenly you have a 42 and a very determined value for that observable? What is the interpretation of that measurement? How do we interpret quantum? How should I understand quantum mechanics and the lack of knowledge a priori about the result of the measurement? In physics, you could not care. Like, if you want, you can do experiments. You can live all your life doing quantum physics without caring about these questions. gets, depending what your take is on this, it could be even worse or better, I guess. You can actually say things about that without thinking much about the collapse of the wave function and all sorts of things and still be okay. That happens in physics. That's normal in physics, as you probably know. All right. How about quantum field theory? Is it better? Is it worse? What do you think? Probably worse. We'll see. So maybe we want to measure localized observables of the field, right? For example, this is a reasonable question, a well-posed question, at least in physics. What is the value of the electric field in this room during the duration of my talk? This is a measurement of a quantum field that is localized in time and space. If you measure it, it's not unthinkable that you get a definite reading. So, for example, 42 volts meter. It's a little bit small, but could be. It's of the order of magnitude of what the real value is. Okay, it's not unthinkable, right? You have a sensor or some whatever, and they tell you 42. Okay, so can you get away with idealized measurements in QFT in the same way that you get away with idealized measurements in quantum mechanics? Let's talk a little bit about that. So Raphael Sorkin wrote a paper in 1992 that claims there's no such thing as idealized measurements in QFT. So I'm going to do a little bit of a historical review that is a little bit particularized to my own experience in the field that I work. I work in a field called relativistic quantum information, and these things are very related to stuff that I do. So I'm going to give you a little bit of a historical, in the context of my field, historical review on this. So Raphael Sorkin wrote this paper titled Impossible Measurements on Quantum Fields. And, OK, but we're going to get to what exactly this paper says. But let me just draw your attention to one thing in the abstract. It is argued that this problem leaves the Hilbert space formulation of quantum field theory with no definite measurement theory. That's the claim, removing whatever advantages it may have seemed to possess vis-a-vis the sum over histories approach. So he's got a little bit of a bias in this paper, as in like, I want to favor one particular way of doing things versus another. I'm not going to get into this. It's super interesting in its own right. I'm not going to get into that. But I am going to focus the attention on, OK, no definite measurement theory. OK, what's going on? Even if you are an instrumentalist and you want to do experiments, you should care about that, because suddenly it's casting doubt on the measurement theory that you used without caring too much in quantum mechanics. So in this paper, he argues that idealized measurements are incompatible with causality, with the causal structure of the theory. And he gives two examples. And the first example, Raphael says, OK, this example already captures the idea. It's a very simplified example with a two-qubit system, so two-dimensional quantum systems. And he says, consider a state, I mean, I'm paraphrasing, it's a little bit more detailed what he says, but consider a state like this, a qubit with, let's say we pick a particular basis, and let's say we start in this state in particular, 0A, 0B. Then perform a local unitary on A, then make an idealized Bell measurement projecting onto this state, okay? And then the expectation of an observable on B gains information about the unitary that you perform on A. And he says that's regardless of the separation between them, space-like, time-like, whatever. Now, maybe you're not very surprised. Are you surprised about that? I am not surprised. Why? Well, because of two, right? Obviously, what you did, what is wrong to do is a non-local projection. You are doing a non-local operation here. So, of course, you're going to transmit information from A to B through doing this. So it's not very surprising, I would say. He says, OK, now let me just do an example in field theory. And says, OK, consider a state rho, and then perform a local unitary on a field observable localized around some area A, make an idealized measurement that is not local on spacetime in a horizontal slice of spacetime, and then the expectation of local observables on B gains information about the unitary on A. Let me just do a drawing. It's much better if I drew it. So you have a local unitary on some localized region of spacetime here on the field, in a localized region of spacetime. Then you carry out, and in particular he does this one, a projection that is delocalized like this on a strip of spacetime. And then he argues that expectations of field observables localized on B know about the unitary that you did on A. So, again, you may not be very surprised because you're doing a very non-local thing here, right? You're breaking causality in a way by doing something very non-local. We'll get there, though. So the paper doesn't get more into that. The paper just argues this. Or my understanding of the paper is that Raphael only argues this in this paper. Now, in my field, people used idealized measurements in quantum fields, both actively and by assumption. On the by assumption here, I included myself as a PhD student, which is when we go into the year 2011 here. I was a PhD student. And in some of my work, I use by assumption the existence. I acknowledge the existence of such measurements. At least they need to exist in order to make sense of some of the claims. And Feydacker, I didn't know about, in the field, we didn't know much about that paper by Raphael Sorkin. And it was pointed out by Feydacker. I'm a fan of Feydacker. You know Fey probably very well. That was called useless qubits in relativistic quantum information. And basically, I draw attention to previous work that shows that the observables corresponding to relativistic quantum field modes commonly employed in papers on RQI cannot be measured by ideal measurements. I saw that paper. Well, many people saw that paper. That's the thing. You call it this, and then the field sees it. Great idea. And I was like, oh, hold on then. We cannot keep doing this. So people, well, basically 3 approaches. When that paper came in, then we all knew about the thing that was going on, and then 3 approaches to the problem appeared, or we took, I guess. Okay, approach 1 is ignoring it. That, I have to acknowledge that. It was sometimes ignore the problem. Approach 1. Not a great approach, I would say. 2 other approaches. Particle detectors, what is that? Okay, we'll talk about that later, because that's going to be the core of the talk. The other one is localized, idealized measurements. And what do I mean by that? Localized, I've done both. Mainly I've done this, but I've done this as well in the past. I don't do it anymore. You see, this is the thing. When we talked about the Sorkin paper, in the qubit example, it was very clear. The problem, the forbidden thing, right, is doing a non-local measurement. The fact that you are invading the light cone of B, right, you're kind of extending the light cone of B by doing a very non-local operation. So the question people did is like, oh, this seems to be the problem, the fact that we are projecting like very non-locally. Can we instead solve the issue by disallowing 2 non-local kinds of measurements, saying, oh, that's not allowed. You cannot violate causality like that, so let's just not. In the qubit example would be, let's restrict ourselves to measurements on local observables and maybe correlations between them. But let's just not do a global measurement, a measurement that is not a local observable. And that seems to solve the problem, right? So, a naive read of Sorkin's paper may suggest that this works. If you just restrict yourself to localizing space and time kind of measurement, you're fine. Any questions? All right. But that's not the end of the story. Let me draw the attention to this paper that you all know. At least based on the talks yesterday, I think this paper is one of the basic ones by Redhead. It's about the Rigveda theorem. But it's kind of nice, huh? The relevance of discussion to the question, what do particle detectors detect? I really love that. I'm going to invert this question. I'm not going to invert this question. I'm going to quote someone who inverts the question and takes the other take to it. It's going to be fun, I hope. In particular, there's a theorem. The thing is that this is not known in RQI. All that I'm telling you about is really not known in RQI. It's kind of known. The point that we are in RQI, I would say on average, people working on RQI, they would say, yeah, we should probably avoid that because problems. So it's kind of controversial. People would say it's kind of controversial to do the localized projective measurement, but why is it controversial and what's the reason? Whether they should stop doing it or not. There's a theorem in this paper, theorem 1 in that paper. it says if P, well, this is the usual notation. We're talking about the localized bounded regions, observables in bounded regions of spacetime. If P is a projector in a bounded region of spacetime, then P is an infinite dimensional projector. So the proof is easy to follow as long as you believe the result of Dirichlet that I haven't fully grasped myself. Maybe people more closer to pure math, if you have read this paper and gone through all the theorems that they use, you understand that very well. Maybe I would love to talk to you about it. But it's basically related. So the logic is very easy, right? The quasi-local algebra associated with an bounded wedge of spacetime is a type 3 factor. Now, of course, any bounded region is internal to some wedge. So by isotony, right, the operators on the bounded region of spacetime is a subalgebra of the wedge algebra. So the projectors in that region are identified with some of the projectors in the wedge, and therefore type 3. And because in a type 3 factor, all the projectors are infinite dimensionals, then all the projectors in a bounded region of spacetime are infinite dimensional. Logic is clear, as long as we accept the theorem. Right, so message to take for my purposes. A projector over a bounded region of spacetime cannot be rank 1. So this idea of idealized measurements that are supposed to model, I got a definite value and then an update through a projector that corresponds to that definite value of the observables, cannot be done in QFT. So no, you cannot localize your projection, because if you localize your projection, fine, you can do it, that's fine, but it does not correspond to an idealized measurement. It will not be an update rule coming from obtaining a 42 in the electric field in this room during the duration of my talk. So that settles it. You cannot do idealized measurements in QFT. End of the story.
You asked to repeat it. Why is it important that the projector in the ideals measurement be rank 1? Because it seems that what's really important is that distinct results are orthogonal. So I might have one projector corresponding to 42, another projector orthogonal to it corresponding to 43.
Right.
But they're both infinite dimensional.
I'll get there.
Okay.
I'll get there. So the point of understanding the idealized measurement as in I have an eigenvalue associated with the observable, and the projector over the space of that eigenvalue.
But it could be an infinite.
Not in this kind of observable. So in the electric field, for example, no. You have a continuum of values, and there's no degenerates. The proper spaces of those eigenvalues are not degenerate.
Continue.
Yep. Anyway, so now what? If we cannot do idealized measurements in QFT, what can we do? Okay, I'm going to say some statements, and you correct me. Because this is what, notice this is the important bit of the phrase. Okay? So you may disagree, and you may be right. Okay? So what do I want from a measurement theory? All right, let's see. Oh.
Try pointing it this way.
All right, so it's the signal not getting there. Cool. We'll test it. All right. We wanted to be capable of producing definite values, like, for example, 42 volts per meter inside the room during the duration of my talk. Uncontroversial? At least, I may have other things. I may have like weak measurements or things that don't give me full information, but at least I need to have that too. So far, so good with your theory. It should give me an update rule. I need to know how, after obtaining that knowledge that the field value is this one, I should be able to update the state. Okay, you tell me, my measurement theory should tell me, okay, what happens to the state after the measurement? Uncontroversial? Okay. It should be consistent with the theory. By that I mean, for example, if your theory is relativistic, you should not ruin the relativistic nature of the theory. You cannot have faster than light signaling based on your update rule. Agreed, everyone? Okay. It should reproduce experiments, right? I can have a fantastic theory like this, but then it should correspond to measurements that people can do in a lab. When people actually measure the field, gets a 42, my measurement theory should be able to model that situation. Agreed, everyone? And that's it. I'm probably, again, I'm not a philosopher of physics. I'm here to learn as well. I'm pretty sure that there are more requirements that some of you, or all of you, or maybe the consensus would be that you need from a measurement theory. But I would be OK with that. Any additions or anything I'm missing? Or
I'm worried about whether 2 and 3 can be consistent.
whether 2 and 3 can be consistent? Yes, and that's the right worry to have, and that's what I'm going to talk about. Yep. Well, I'm going to talk about a bit. Yeah, that's great. All right. Is there an alternative? Oh, sorry. Play that you didn't see that. Is there an alternative to idealized measurement? All right, I'm going to try to convince you that there is. And see what happens. That has all these things, and it's fine. All of them are fine, are compatible. All right, let me introduce the notion of particle detector. Particle detectors are aliens, in a way, to quantum field theory. But let's see. What's a particle detector? So you see, how do we measure quantum fields, like for real, in the lab or in our lives? We're measuring quantum fields all the time. We're looking at things, right? We are measuring the electromagnetic field when we see things all the time. Okay? We get excitations of the electromagnetic field that get to our eyes, and our eyes measure them. The apparatus composed of eyes, the nervous system that transmits the information, and the brain measures the field. So, that's the way we measure quantum fields. There's no other way. So particle detectors, and let me argue, though, what I'm going to define as a particle detector. I'm going to call it a non-relativistic quantum system that couples locally to a quantum field. By locally, I mean, OK, a particle detector is some non-relativistic quantum system for me, like think of an atom, for example. And by non-relativistic, I mean non-relativistic approximations are really good to describe the physics of those objects. And it couples locally in time and space to the field. The coupling, of course, is not any coupling. The coupling has to respect causality of the theory. If you do it from first principle, we'll talk a little bit about one example of this. And this is kind of inverting the question in the abstract of the Red Hat paper. This is Bill Unruh. And I'm quoting Bill Unruh, says it many times, but also in a paper, it's Bill Unruh and Wald, when they talk about the Unruh effect. And they talk about Rindler excitations. And the Rindler excitations, paraphrasing again, Rindler excitations don't make that much sense. Because after all, particles are, you cannot give them the ontology of particle to a Rindler excitation. People were discussing the Unruh effect when they talk about particle creation when you have an accelerated observer, right? And they discuss in that paper, well, actually, giving it ontology of particles is not OK, because after all, particles are whatever particle detectors detect. That's what Unruh said. We will get there. It's a little bit. But it's kind of inverting so you see, Red Hat was asking, oh, what do particle detectors detect? And they say, no, particle detectors, by definition, detect particles. I will talk more about that, but I wanted to put it out there. Yes. All right, so let me give you a particular model of detectors, which is the Unruh DeWitt model. It's a very simplified model, a two-level quantum system coupling locally to a quantum field amplitude, or maybe it's conjugate momentum. So the Hamiltonian looks a little bit like this thing here. It's a scalar field, very simplified model. A little bit like that. So let's see what this is. We have a coupling strength. We have a switching function that controls how long the interaction is on. We have some internal degree of freedom of the non-relativistic system, what I call the detector. And it couples to the field smeared. By the way, important. So tau psi is the center of mass proper frame of the detector. And Tx is the quantization frame. Just pick a frame in which you quantize the field. OK? Right, so you have the quantum field. You have, keep in mind, this is the smearing function. So this tells you the extension in space of the interaction. And this tells you the extension in time of the interaction. But you see, it's coupling an internal degree of freedom of the detector with the quantum field, linear coupling. We can simplify a little bit, because if we write T and X of the quantization frame in terms of tau and psi, you can just write it a little bit like that. It's a shorthand notation. And let's consider a very simple case, because this, of course, is an arbitrary trajectory of a detector that's following an arbitrary trajectory in spacetime. that there are issues that you may have if you're a relativist, right? As in like, by relativist, I mean like if you like relativity. So sorry, I not remember that. I'm in philosophy. You may say, oh, but hold on, extended. So if it's a detector, can you accelerate that if it's an extended object and so on? This assumes something called Fermi-Walker rigidity, which is from the center of mass frame, the distance to every point in the detector is constant. So I have tension. I have like forces that sustain my detector. So not every point of the detector accelerates at the same rate. Okay? That happens with an atom. Anyway, we will talk about what this is really later on. Anyway, so let's consider a simple case, a stationary detector in the quantization frame. So things simplify a lot. In the quantization frame, we just have that. So the quantization frame and the proper frame of the center of mass of the detector are the same. And then you can tell this is the form of the Hamiltonian. And nice enough, you can write the unitary evolution generated by that Hamiltonian as follows, where you have a space-time integral, which is nice. This is, if this is explicitly covariant, if we will talk a little bit about that. This is a scalar, right? This is explicitly covariant. Interpretation. You have three options, I guess. I'm going to talk about two and mention the third one. Maybe I'll start with option 0. Option 0. This is an interaction between a detector and a field. Nothing belongs to anything. As in, like, this is just the interaction. The field and the detector, you cannot separate them really. These things, the interaction belongs to both. It's not really, the mirroring and the switching are not part of the detector or part of the field. They're just part of the interaction that you have. That's option 0. Option 1. I can rewrite this unitary like this. What did I do here? So I have a switching function. I call this a monopole moment, or monopole field, if you want. It's a non-relativistic field. There you go. You got a non-relativistic field here. Monopole field and the quantum field that is relativistic. And of course, the monopole field is just the evolution of the internal degree of freedom of the detector and the smearing. So the smearing here, writing it like that feels like the smearing belongs to the detector. Detector has some extension, right? And I could have even put the switching inside. I could have, and I said the detector has some time extension, some existence in time, and then lives somewhere in space. Okay? Maybe I should have put the switching in there. Option 2. Oh, I can write like this, though. I can write the internal degree of freedom of the detector coupling to a localized observable in space and time of the field. And in that sense, if you want, the smearing and the switching don't belong to the detector as much as they belong to the observable that the detector is measuring. I'm coupling this internal degree of freedom of the detector to some localized observable in the field. There's a choice. You have this unitary evolution, and you choose how to interpret it, right? So nothing bad with one or the other. It's interpretational, if you want. Questions? All right. So what do we have so far? So we have a particle detector that couples, a particle detector model, right? Couples non-relativistic quantum mechanical degrees of freedom to a local field observable. And I chose to go, let's say, interpretation 2. And I can say that statement. Oh, yeah, the model, that model is just get an internal degree of freedom, some quantum mechanical object, and couple it to a localized field observable. Causality with those models are OK. These things do not violate causality. Question?
Their violation of causality is exponentially suppressed.
It depends. So if you look at, you can actually point like localized, and then it's fully causal.
Sure.
And of course, it's extended. So what Emma is pointing out is that this detector is smeared in space. And of course, that smearing in space, right, is a non-locality. It's coupling at the same time to different points in space. So in that sense, it's non-local. But as opposed to measuring with a projective measurement, that non-locality doesn't exist far away from the extension of the detector, which is what Emma was saying as well. If you pick a smearing function that is well-behaved enough, then you're guaranteed that causality violations that would come from that are exponentially suppressed, and you can make them as small as you want. So it's a very operational way, even if it's a smear detector. Again, I could just forego completely the discussion by saying particle detectors are point-like objects, and that this F is a delta now, and then we're fine. Because then there's no violation of causality. It's the same way as localizing the projective measurement, same thing. You can localize at a point, and deal with divergences, or you can localize in an extended region and then say, okay, I'm going to have some non-locality, but it's under control. That's the key point. Okay, I can get all the signaling contributions below whatever threshold you want. So in that sense, it's a control way of violating causality. Good point. More questions? It's a bit of a technical point, but it's a good point. Okay, so causality is okay in the sense of these things don't have the problems of projective measurements. The coupling is covariant, so there's no problem with the causality of the theory. Now the question is this model just a toy? It was introduced. Question?
Yeah, well, so you said the coupling is covariant. Does that depend on the form of the smearing function at all?
In the sense that Emma said. So if the smearing function is a point, right, then it's fully covariant and there's no violations of causality coming from that. If you have a smear detector, then you're going to have, that transforms as well under changes of coordinates, but transforms covariantly. You still have non-local signaling in the sense that you're extended in space, right? But it's covariant indeed. The way in which it transforms, you pick up factors that are related with the Jacobian of the coordinate transformation, and then the switching and smearing mix. So your interpretation of what is the switching and what's the smearing will change in different frames, but the transformations are covariant, yeah. That, for example, transition probabilities with those detectors do not depend on the reference frame. So you can compute the dynamics of those detectors, and I can give you a paper where this is done as well. I don't have it here, but you can compute the response of that detector as seen in the lab frame, the response of that detector computed in the detector's proper frame, and the probability is invariant on the change of frame. So it is definitely covariant. The predictions of that model are covariant.
But what about the Hamiltonian?
Oh, it changes. Yeah, no, the Hamiltonian is not a covariant quantity. Keep in mind, good question. The Hamiltonian is certainly not a scalar, not a vector. The Hamiltonian is a component, if you want, of a 4-vector, or depending how you say it, but a component of a 4-vector. This thing, though, this is the thing that you should look at. This thing connects a Cauchy surface in the past with a Cauchy surface in the future. If you do a coordinate transformation there, you may tilt those Cauchy surfaces. But this U, the map that goes from one to another is invariant. So if you do a reparametrization of coordinates here, because you are integrating over space-time, and the unitary evolution is the same. Okay? So yeah, the Hamiltonian is certainly not covariant, but that doesn't mean the predictions are not covariant. That's true for any theory. All right, so my point here is this model just a toy? Something that we used to play, or is it representing something that has physical existence for a physicist? Again, important for a physicist. Okay, let's look at a model that is used in atomic physics. The model that is used in atomic physics. Coupling electrons in an atom to the electromagnetic field through dipolar coupling, dipolar electric coupling. That's the Hamiltonian. The Hamiltonian is d times c. So E times the x, center of mass of, x is the degree of freedom of the position degree of freedom of the electron in the atom and couples to the electric field. You can do it for many levels, that's no problem, because but just because the Unruh DeWitt, the simplest version is 2 levels, let me just reduce to 2 levels of interest. That doesn't change anything. I can do the same thing with many levels and generalize the Unruh DeWitt to many levels. Nothing changes. Separated by an energy gap, omega. Right. You can write this operator in terms of its matrix elements. Notice that I didn't write the diagonal ones. The diagonal ones cancel because of parity. I don't have the detail here. But for this operator, you cannot connect the same level. This is just interaction picture, this operator in the interaction picture. With all the matrix elements, the diagonal ones not written because they're 0. We introduce spectral decomposition of identity in the basis of the position operator, which I don't want to call eigenbasis. And then we introduce it basically here and here, twice here and here. And after introducing that, you get that this Hamiltonian, now taking this position representation, takes this form. With this F smearing vector, okay, this is a vector theory, not a scalar theory. This smearing vector is the product of the excited state wave function, the ground state wave function, and X. Introducing time dependence in the coupling, you get a switching function like that, right? And then we can compare We can write the Hamiltonian like this. Oh, this is just a translation. You can ignore that one. The Hamiltonian is like this. It's a dipole coupled to the electric field, of course. Now, the only thing that I did here is take a position representation for the center of mass, degree of freedom of the electron. And the Hamiltonian looks like that, a dipole coupled to the electric field. Okay? And this dipole operator has some smearing internally that is related to the wave functions of the ground and excited state. So it lives where the atom lives. So this detector, the model of atomic physics is telling you the atom sees the field where the atom lives. And where does the atom live? Well, it lives depends, partially on the excited, partially in the ground state, and there's an X there. This is where it lives. These things are exponentially suppressed, of course. Right, so you can compare the electromagnetic dipole coupling. That's a semi-first principles in the sense of atomic physics Hamiltonian, where the Unruh DeWitt model. And you can tell, here I wrote it in this convention, if you want, where I put the smearing into the monopole, so I get the monopole field. And you see that the Unruh DeWitt coupling is just the scalar version of the electromagnetic dipole coupling. Just replace the vector field here with scalar field. So, in fact, the Unruh DeWitt model is still more advanced than what people use in labs of quantum optics. They do simplifications in quantum optics. One of them is the scalar simplification. They do many more. All right. So the Unruh DeWitt model captures fundamental features of the light-matter interaction when, of course, the exchange of angular momentum is not relevant. The vector nature of the field is not relevant. If you want to read more about it, you can do here. There are the places after that, but this is, I think it's a good discussion to begin. Right, I was saying, in fact, simplifications of this model, the Unruh DeWitt meaning, are used in quantum optics experiment. There's the Glauber detection model. The Glauber detection model uses the Unruh DeWitt coupling after a couple more simplifications. That are very bad for causality, by the way. One of them is called rotating wave approximation. The other one is called single mode approximation. Sometimes they don't do single mode, but do rotating wave, and they shouldn't, because they're like the same kind of approximation. But the point is that this Glauber model that is used, and people use and seems to work, of course, you see, and your question again, the Glauber model satisfies 3 out of 4. It's not respectful with the causality of the theory. It trashes the causal structure of the theory. It's not relativistic in that sense. So, yeah. Oh, 5 minutes. Oh, wow, okay. Right, okay. Then let's just get there. So extracting, okay, fine. So the Unruh DeWitt coupling here can be used, right, to measure a quantum field. It's a particle detector. Let me give you a protocol with this model. So getting the 42, that number. First, we couple the detector to the field in this room. We have a detector, and we couple it to the field. Second, we do an idealized measurement on the detector. That is kind of okay, because the detector, remember, was by definition a non-relativistic system. So no problems with doing projective measurements in that detector. Of course, there's an update rule. Update the field state with a consistent POVM compatible with the outcome. That thing will be localized, the detector are localized. That thing will not be a projection. It will be maybe a set of projections. It will be a POVM on the field. So remember, what we do is couple the detector to the field, idealize measurement on the detector, update rule on the field. Causality is fine when you do that. Well, and there's some couple more assumptions, but if you want to read more about it, maybe you know this paper that Chris Fuster wrote about it. Causality is fine. I have an asterisk for a reason. But this kind of model in which I couple the detector, the coupling is covariant. I obtain information from the detector doing an idealized measurement on the detector, and I update the field through the POVM that comes updating the information about the field after measuring the detector. That thing respects causality. Okay, reviewing what I wanted, from a measurement theory. I wanted capable of producing definite values, giving me an update rule that is consistent with the theory and reproduces experiment. Okay, particle detectors are non-relativistic quantum systems, so idealized measurements of the detector after the coupling exist and yield definite values. You can get a 42 out of looking at the detector. The update rule, idealized measurement of the detector induce POVMs update rules on the field, POVMs that are that respect causality. The references before. Fuster, I would recommend to read the Fuster one. Particle detectors are realistic ways of modeling the measurement of quantum fields. In fact, they do reproduce experiments. Like Glover, for example, the model of light detection. If you don't do the approximation, you get another model that like Glover is an approximation to, but the real model gives you and reproduces the experimental outcomes. So I would argue that those POVMs that are induced in the quantum field theory through the use of particle detectors are a valid measurement theory. And the quotes are because it's according to my criteria. Oh, no, there's one more. Yeah. Now, one could remove the detectors from the picture. If you want, now that you have that, you can remove the detectors from the picture. You can just focus on the POVMs. The detector, all this detector formalism just yielded a set of POVMs. And you see the detector is an alien to this theory. The detector is something non-relativistic that I brought into the relativistic theory. But now that I have the update rules and the POVMs that do that, that associate definite values or outcomes of measurements with update rules on the field that respect causality and reproduce experiments, I can just trash, if I want, the particle detectors from the picture. So and just be left with the POVMs that emerge from the detector interaction plus measurement. And they can yield definite values associated with experiments, provide an update rule that is consistent with experiments and not faster than light signaling. So maybe this is a valid measurement theory. Keep in mind, I trust the detectors. I have just a set of POVMs I give you, I prescribe to you. This is how you do measurements on field. These POVMs that yield these values and update the field that way. So you're measuring the field in this area, I'll give you the set of POVMs. So just to summarize the last slide. So idealized measurements directly are not possible in a QFT. Coupling detectors and performing idealized measurements on them, that you can do. That's no problem. Provides measurement outcomes and update rules that model experiments. So maybe we can replace prescriptions based on field theory by the POVMs, prescriptions that use idealized. Oh, I can measure this observable and it gives me this definite value. Maybe I can replace that by the POVMs induced by detection and idealized measurements on detectors. So I guess my claim is that reproduces experiment and preserves causality. So maybe it's a serious, maybe not, and hopefully you will tell me, but maybe this is a serious measurement theory to consider. That's it. Thank you.
We have time for discussion. The rule is if you have a question, raise your hand and I'll try and keep a queue. If you have a comment on what's going on, raise a finger and we'll jump you ahead in the queue. And students get priority over faculty. Don't tell me no one has comments.
Students from anywhere, right?
Yeah. Sure. I can't believe that Laura's qualms about compatibility, update, and causality have been completely. Okay, there's back. Yeah, Stefan.
Yeah, thanks. This might be a clarification question only. When you say that detectors are non-relativistic, I think I understood the context in which you were saying that. And maybe this is a very naive question, but what if you just change your frame of reference? Then you cannot apply this theory?
You can. So by detectors being non-relativistic, I mean that those detectors are not, so if you check this monopole moment field that I had there, is not a relativistic field. So that thing doesn't transform as a relativistic object. It's not a scalar, for example. The unitary evolution between two Cauchy surfaces, for the field and detector here, field detector here, is invariant under Lorentz transformations, and the generalized transformations if you were in curved spacetime. So the predictions of the model are relativistic, are covariant, okay? The detector model in itself is not a quantum field. Now, if you go to the Fuster paper that I cited, Fuster generalizes this to arbitrary detectors that are field theories that can or cannot be relativistic. Okay, but all that I mean is that the detector in itself, think of the example of the atom. In atomic physics, I had a Hamiltonian that is p squared divided by 2m plus some Coulomb potential, right? That is certainly not relativistic. And that generates the structure of particle detector. You see, so it's a non-relativistic system. There's no assumptions on the detector being a relativistic system, okay? In general, you could have detectors that are relativistic, but I'm not assuming that. And keep in mind that in the one that I use, if you have a smearing that is not, if it's a point-like detector, then you can think of it as relativistic if you want. Definitely, it's a particle that is a relativistic thing. It lives in no, it's not relativistic, it's a particle. So it's not quantum relativistic. It's kind of first, let me say this, first quantized. Are you happy with that? The detector is a first quantized thing. I don't care much about the field nature of it. But that doesn't mean that the model is not valid and that picks a frame. The model doesn't pick a frame. You can describe the predictions of the model from any frame you want, and you get the same predictions if they're scalar predictions. And they transform properly if they're vector predictions or something like that.
So if you can do away with detectors and just use the POVMs induced by detectors in order to perform measurements, what is recording the information that results from the measurement?
That question is, so to see if I understood this question, would you ask the same about projective measurements in a quantum mechanical experiment? Because that's the thing, right? In a measurement theory, they don't care as much how you obtained it, but rather how, knowing the result of the outcome somehow, you wrote on the notepad, you have knowledge about it, how you update the state.
I think I still care about it in this context.
Okay, so when I presented this, I meant, okay, how to build a measurement theory that, given the knowledge that the value is this, updates the field state. Now, if you ask me, how do you measure that? I say, oh, definitely with particle detectors. So if you ask me, I would take a step back and say, don't do away with the detectors. Doing away with the detectors is just to build a measurement theory that is self-contained within the QFT. That is based on the premise of, I know that the field is 42, and therefore, in this area, therefore, this is how I update the field, compatible with that. But it's definitely particle detectors who do the measurements, yeah. Doesn't transcend the particle detectors, that's what you're going after.
Yes, no.
So this was really interesting. I feel like there's a sort of parallel objection that comes from like the measurement problem. So you can imagine, say, I'm going to give a measurement theory for ordinary quantum mechanics that involves the coupling of a quantum system to a system that I can approximately treat classically. And then you get a theory going on, and you show that it works, and voila. And this is going to work in the physics lab. It's not going to please philosophers, because until you have a story about how that approximately classical system emerges from the thing that you think is ultimately quantum mechanical, it's not a kind of fundamental story. And so there seems to be a parallel issue here, which is, you've got this patently non-relativistic quantum system that's the detector, and at the end we kind of forget that it's there, but it still seems like it was important to kind of get the mathematical structure of it.
Right.
So I guess, is there a sense in which you could try to tell the entire story without that from the beginning, like using, exponentially smeared quasi-local operators in HUFT, and maybe we have to use this kind of procedure to figure out which ones we can actually measure?
That connects with Emma's question. So I tried to dodge it, but I'm not going to dodge it anymore. When there are two questions about it, my belief is that there is. My belief is that you can actually talk about it in terms of AQFT, and that's what Chris Fuster also is aiming towards. Chris Fuster is also inspired, I believe, Chris Fuster is also inspired by detector models. With detector models that are like that, I can build a theory for you. I have the expertise to do that. How to generalize this and express only in terms of AQFT notions, and maybe talk about a new ontology coming from it or not, that depends. That's something that I believe can be done. But for now, all I can tell you is that I can prescribe for you experiment compatible measures, all these four things, right? All these four things that I had. Maybe if you add a fifth one, as in like, no, I require to understand it from the point of view of an ontology in AQFT. If you require that, I don't have that. For now, I can give you a measurement theory that is covariant, compatible with experiments, gives you update rules, and compatible with definite outcomes of measurements. These things I can give you. But this is really good. It's what both Emma and you, I think, are asking the same thing.
Laura?
I thought I saw Ben's hand up.
You guys had your hands up at almost exactly the same time. So let's be Laura.
That's an observer-dependent statement.
Right, yeah. But here. As chair, I'm going to go with Laura, and then Ben, then Adam.
So this is maybe the same point as Emma's and Noel's, dressed up differently.
Go for it.
It's on the forum. What do RQI people think of the following? So the protocols usually seem to start with you got some qubits in the state.
Sorry, what?
The protocols, the various protocols you care about, the first step is you got some qubits in some state. And the standard story about how you go about getting a quantum system into a state appeals to the kind of idealized measurements we haven't got in AQFT. We've got an electron in the spin-up state that's, we passed it through a Stern Gerlach magnet and got deflected off, was rejected onto that outcome. So is there any anxiety, concern about how it is we come to have relativistic systems and the sorts of states we need to know they're in to embark on the kinds of manipulations on them we're studying?
Good question. I think I cannot speak on behalf of the RQI community.
What do you think?
Also because RQI community is extremely diverse in terms of you have in RQI you have people coming from field theory, you have people coming from relativity, you have people coming from quantum info, and maybe these are the ones that you're talking most about. But no, still this is an issue for all of us. It is definitely an issue. I would say that some people would not care about it. It's like, well, you see, we have an empirical truth, which is I seem to be able to prepare those states. And I start from there. Assuming that I can do it, I start from there. Now, the issue that you raise is actually a big one. And in fact, there are something that has not just, if you want, a metaphysical value, but also has even sometimes empirical value in the sense of assumptions that when people place qubits in spacetime, that happens, as you say. People say, the qubit lives here. That's not something that you can do. And in fact, if you talk about quantum communication in space-time, and then you start with a relatively localized information contained, say, in a particle detector, which is, say, an atom. Huh? You have an atom that is relatively localized. And by relatively, I mean what I call the notion of strongly supported in an area. So it's not compact support, but it's like very strongly suppressed outside of an area. And then you ask, okay, the quantum information contained in that, where can that go? Peter, in particular, who's here, also is a student that worked on that with me and with Ahinkamp and Ida. Where does the information go? And can you send that quantum information to a particular person that lives somewhere else? And if you think of this nice picture of qubits, then it seems easy that you can. But no, you can't. And the reason you can't actually is related with the relativistic nature of the localization of information. So again, I didn't answer your question. Your question is valid. It's a question that we should care about. How do you get to the starting point, if you say, when you have a localized container of information, say an atom, right? It's something that is taken in RQI, I feel, in RQI as a given. We do care about, once you have that, what happens with that localization, and how does the relativistic nature of the field affect your ability to send that information, to talk about that information even in this area. For example, if you ask me, there's no such notion of particle for me at all. I'm of the opinion that we should banish completely the notion of particle in modern physics. We do care about that. We do start from a point in which you have something. Sometimes it's a vacuum state, so maybe talking about ground states is easier, less anxiety kind of thing, generating. Sometimes we start from ground states of everything. But sometimes we don't. Sometimes we have information somewhere. And usually we start from the point that we encoded it in a quantum system that is easy to encode, and we take the empirical, if you want, the empirical truth, let me call it that, of experimentalists telling me, I can prepare that state that you wrote there, something I can do. So yes, great question. Open, I think it's still an open thing, right? How do you get to the point, how do you concentrate information? I'm working on things that are related to that, as in like, related with looking at things that come from like area laws in many body systems and quantum fields. Can you imagine that you have the ground state, right? And then you pick a region of that ground state, a region in space-time. Can you compress the information and localize that information in a particular region? Can you do something called entropy compression in those systems? And it's what's the process? What is the kind of unitaries that allow you to do that? And are they physical? Do they make sense? So I guess we're approaching that question in different directions. I can talk about what I do. Again, I'm not sure about what other people do in that regard. But I think it's still an open question, and it's an important one.
Ben's next.
Yeah, so I wanted to basically ask again the question that Wayne asked at the beginning of the talk, which was like why this is the way that you motivated the detector model was by saying, because we can't do the localized projection thing, and the reason was because we were worried about not having rank 1 projections. And so, yeah, I was confused why we should care about that, because like even in a non-relativistic measurement setting, if your variable has like take on continuum values, then none of the projections that you're really interested in are rank 1 if you're associating them with the measurements. And there's something like measurements of position, like I don't care.
Well, if you get a 3, so that's the possibility of yielding a single value, right? If you get a 3, the projector is rank 1.
Yeah, but
No.
but for variables that have continuously many values, you don't need to get an actual answer. You just need to have an answer within some error bounds.
Fair enough. Then, so I took that to introduce again. That doesn't affect any of what comes after.
Well,
But
actually, I'm not sure it does because I think then I was wondering, like, okay, so at the end, you didn't show us these POVMs that you get,
No.
Or what they look like, but are those localized? Because then if they are, like, how do they compare?
They are localized. They are not projectors.
Okay.
That's the point. The POVMs that you get out of that are definitely not projectors. Yeah, their rule is not. So okay, that's a good point. So what happens if I extend a little bit my tolerance to have some uncertainty in the result? Then it's definitely an infinite dimensional projector now. And then I'm not being as I don't know, as mean as to say, okay, I want a value and that's why it doesn't work. There are two branches. One is, okay, if I allow for a little bit of error, how does that affect the causality of the problem? Does it introduce signaling outside of the light cone that is not exponentially suppressed? The answer to that is, in some cases that I checked, yes. So it's a bad kind of signaling if you do that. The second question regarding if you forget about that point to motivate, and I motivate somewhere else, when you interact with detectors on quantum fields, can I approximate that interaction as a projection? You see what I mean? Even an infinite dimensional one. Can I? What is really the update rule that I get on the field when I couple a detector? And the answer is certainly not a projector. Not a finite dimensional one, not an infinite dimensional one. What you get is a POVM that is not a projector. So the update rule associated with coupling a detector, measuring later the detector getting a 3, and updating the field consistently with that is not a projection of any rank. So I guess I could have motivated it like that as well, alternatively. But I think it's an important point here. If you localize projective measurements, and assuming that you're not going to have a definite value outcome, but you're going to have a range of outcomes, you still introduce illness in the faster than light signal, and in particular, illness that doesn't get suppressed or it gets suppressed polynomially. That statement is dimension dependent too. Depending on the dimensions of your spacetime, you may be able to do better with a localized measurement in which you don't know the answer and it's within a rank of possible answers. So it's still an open question. So it's something that we should look into. Like how does and we are kind of looking into. I know some cases in which it's really ill. That's all I can tell you. Some cases when you update, for example, if you measure the amplitude of the scalar field and you tolerate measurements of the amplitude that are a little bit uncertain, say an uncertainty delta, right? And then you have this projector that now you can localize in space and time, you still get polynomial violations of causality. Basically, you get something that is very localized, but then weighted by 1 over x minus y, integrated also over y in the whole spacetime. So you get polynomial tails coming out of that. But yeah, no, good question. Both a good question.
Adam's next.
Yeah, my question was probably closely related to Laura's as well.
So, sorry.
My question is closely related to Laura's,
Okay.
I think, but kind of from a different angle. So when your detector gets a particular value and then you update the field, what does that field configuration look like? Is it anything that you could say, okay, there's a definite value in this room and something elsewhere, or is it?
No, it's slightly different. So, you're asking me to I was hoping to avoid this. So what you get when you couple a detector in a localized area, if you look at the field, what is the field like? The field has so imagine that pick your favorite observable. For example, I don't know. Say if the detector is in the ground state, it's particularly simple because if the detector is in the ground state and you couple it to, say even simplest case, detector in the ground state, field in the ground state. You see, if you do the approximations that quantum opticians do, the detector will not detect anything. It does though, because it's a localized measurement, obviously. It's not a global, it doesn't detect anything if you were able to measure the whole thing in the whole space and time. But if you localize it, you get some clicks of the detector. The detector registers an outcome. So when you do the update rule there, what you get is pick your favorite observable, pick the phi square, the amplitude square, or pick the stress energy density. You get a bump in the area where the detector did the measurement. And that evolves in a particular way. And that the way in which it evolves has a little bit of coherent superposition and a little bit of incoherent superposition too. So you create a state that is pretty non-classical in many ways. And also it's pretty non-particle in the sense that it's a superposition of things that people would call particles, if you want. And again, both. It's a mixture of coherent superpositions of what people would call particle excitations. So So it's not trivial. It's localized though. And of course, if you let it evolve, it goes away on the light cone and more depending on the dimensions.
You had your hand up next.
Yeah, so I just have a little concern about how well defined your protocol is to go from a measurement value to an updated state of the field. So let's say that you get a measurement value of 42 volts per meter. First of all, that's 42 volts per meter in a certain direction.
Yeah, of course.
That's a detail. So you get that value of 42. Now, from what I understand, your interpretation of that as a physicist is that you had some detector coupled to the field, and then that detector somehow obtained a value of 42, and now you just discard the detector and you update the field based on the POVM that you get. But as you detailed in your talk, your detector depends on several parameters, like its smearing function, switching function, what's observable you're coupling. I can imagine that I can have two different detectors with two different smearing functions, switching functions, everything, that both give the same value of 42. So how do I know which one of those to pick in order to update my field? It doesn't seem like it's a well-defined procedure.
Very good question. Really good. The smearing and the switching don't concern me as much, because the smearing and the switching are part of what region in spacetime you are measuring. So the smearing and the switching will not be model dependent in that sense. It's basically, my detector is this big, so it's measuring the field in the extension of the detector. So I'm not really measuring the whole room, I'm measuring here. That's the information included in the smearing and the switching. You could have asked though, you couple linearly, okay, the observable, you said the observable. The observable also doesn't worry me, because the observable is what you are measuring of the field. Your choice of observable is, I'm measuring the amplitude of the electric field in this direction, and actually, if I pick this direction, I'm pretty sure that 42 is a very reasonable value, because it's 100, in the radial direction is 100, so 42 something like this, something like that. So the observable that you pick is precisely what you are measuring.
So are you talking about the field observable or the qubit observable?
The field observable.
I'm talking about the qubit observable.
Okay, we'll get there. The field observable. So all those things, don't worry. That's why I'm first addressing the ones that I don't worry about. I don't worry about the switching and the smearing and the field observable. This is exactly your measurement. This is what you're measuring. Now, your question is, okay, what happens with the things that are detector dependent? Because it's thinkable that the POVM that you get depends on the dimension of the degree of freedom that you are considering of the detector. It may also depend on the energy gap between the levels of the detector. It may also depend on the coupling strength, right? So this is kind of cool, because it kind of like connects with like, okay, fine, if we take the empiricist approach, we say, okay, all the physics that there are outcomes of detections, then definitely the choice of detectors is important. And keep in mind, I don't use, to measure the electric field, I don't use, I need to do some tricks. So I guess the fact that I'm not factoring this is a linear coupling. So it's literally, if you want, it's like the usual detector model, right? In which you have a pointer variable and you couple it linearly to the observable that you're measuring. But you can think, what happens if I couple quadratically? It's not unthinkable that if I couple quadratically, of course, the outcome of the detector will not be 42 because I'm not measuring this observable, but with some math later on, post-processing the outcome measurement, I may get a 42, as in like, well, if the outcome is if the outcome is the square of 42, maybe that means that is 42, the real value. So if you don't couple linearly, you need post-processing of the data. The post-processing of the data, if you don't couple it linearly, would factor into the POVMs that you get. So that's adding extra structure. It's a really valid question because it talks about what's the ontology of those detectors really. But the thing is that I would argue and I would expect, and you use a different detector model, you're not going to get a direct, I could distinguish between direct readings, some variable that is a pointer variable that really couples linearly to what you're measuring, and indirect readings. I couple to a different variable, not the one I'm measuring, but I can induce the value of that for post-processing the outcome that I get. I would expect, if this is well defined, that I'm doing that, factoring in the POVMs on the field, the post-processing that you have, then you should get something compatible with the 42 of the linear detector. Maybe with more things, because measuring the square of the field amplitude is not the same as measuring the linear part. Your nuances that you get that you're ignoring, but you couple quadratically and so on. So maybe interesting things will come out. But this is a really good question. Dependence on the detector model. If I do away with if I don't do away with the detector model, that's fine, because it's part of my theory. These are the detectors I call physical. If I do away with them, you can ask what you ask, like how does that depend on the detector model? I would say it should not depend once you factor the diversity of detection in the POVM.
what sense you say you don't care so much about the smearing and the switching?
Well, I care, but it's not dependent on the model.
Yeah, but so in what sense, like, is it, but sometimes I don't know in what sense, like, the response is like, these are choices that go into the model and matter, right?
Yeah.
And people can make different choices.
I would take in option 2, right? That goes in the choice of observable of the field that you're measuring. So you see the observable of the field that you're measuring?
So in option 2, I understand that the detector is coupled to a smeared field of field.
Precisely.
So, but then the smearing remains a choice.
Yes.
In the model.
Yeah, but it's a choice of the variable that you're measuring. So there are 2 choices to make. My detector and the variable that I'm measuring, right? So varying the smearing and the switching is varying the observable that I'm measuring. Different switchings and smearing means that I'm measuring perhaps the electric field in this room, or the electric field in my hand, or the electric field in a region like this, and for how long I'm measuring. So it's a choice of the observable you probe.
So maybe this way of phrasing it becomes more problematic in option 1, because then it could be different detectors that you're coupling to kind of make the same thing at the...
Yeah, but if you do away with the detectors, it makes more sense to So these are not alternative.
I like option 2.
Yeah, I know. Yes. I have this option 2 because of you, and option 0 because of Emma. The option 2 here is the one that makes sense on, like, what are you measuring with the detector? If you ask me, what does the detector measure? I will tell you, oh yeah, this smeared observable here. Again, keep in mind that these are choices. It's how you decide. The true evolution doesn't care of your choices. It's this. Then you can decide to ascribe the switching and the smearing to whoever you want. An atomic physicist probably would tell you, no, they belong to the atom. And then a field theorist would tell you, no, they belong to the smear observable that you are measuring. But those are choices.
But so in the way you phrased it before, do you imply that given a particular situation, these choices are pretty much fixed? Because
No.
Like,
Give me a problem. I want to measure the electric field where? Well, here. Then I give you, okay. Then I pick my smearing and the switching to cover that. So it's a choice on the field, if you want, not a choice on the detector. And then find a detector that lives here for that amount of time, right?
but even though you said you talked about option 2, then when you were showing this detector being like this, I don't know, rigid body thing like this.
I never showed.
You saw the detector. What was that thing?
Never.
Oh, what?
When?
Oh, I saw something that looked like a nail or something. I didn't understand what it
Oh,
was.
that thing. That was supposed to amuse people. But not.
What was it?
It's a photo detector.
I thought detector, right?
Yeah.
So some kind of detector which
Sorry.
can be like literally a rigid body, no?
That's a photo detector. Where is the photo detector? There you go.
Yeah, okay, so this kind
That's
of...
a real one. This is a comedic one. Kind of.
Right, so maybe the previous one. Okay, so that's like a realistic situation.
Yeah, very realistic.
Yeah. So, okay, because it seems that like notions of macroscopicity going on.
Oh, yeah.
In some sense that the detector is a macroscopic system that you pretty much can know where you couple it to the field kind of thing. So would you think that in such situations at least the smearing is kind of given by that in option 1?
Right, good question. As in, like, the assumptions of this detector model assume that you have 1 degree of freedom that lives in that smearing. Okay, that's a really good question. Would it happen, instead of having 1 single detector that lives in this whole thing, you have many, many, many detectors that live in here and coupled to the field? The answer is that would change the detector model, but it would not change what it's coupling to. So this can be done. I can have an array of detectors, many of them, that couple to the field collectively. That's not difficult. So that's not difficult to write, to pose as a problem. It's difficult to do the math about it and get outcomes out of it. But that's something that can be done. And it changes a little bit because you can get coherent excitations collectively, and you can get, if you assume the model, a Geiger counter would be the same. If we only had Geiger counters, right, this is what people in the past started using to count particles. If you had a Geiger counter, right, that thing pretty much acts like a single atom, as I said. Because what they do, they have many atoms for sure, but then when there's a particle that excites an electron on that atom, that gets photomultiplied, as in like that thing, the electron goes away and starts to be accelerated through a potential fold. So this is like many, many atoms. One of them at least gets excited and amplified. That's the point. So in that sense, it's just the particular atom that got excited that does the measurement. Now, that, of course, that kind of model for the Geiger counter neglects, oh, but hold on, you can have because of this evolution, you can have superpositions of the first atom going on or the second atom going on. Coherent superpositions of that. If you have that, the outcome changes. And that is not in the that can be modeled it wouldn't be 1 degree of freedom mu of a single detector. It would be a bunch of degrees of freedom of that lattice of detectors, right, that couple to it. And you can get collective excitations for sure. That will change the detector model. But the basics of what I say will not change. That's just changing in a way what observable you're coupling. And it would be more difficult to model the macroscopicity of this, right? As in, like, when you have only one quantum, I don't think there's anything magical from the micro to macro. I just don't think so. I can keep adding microscopic systems, and I would get emergent macroscopic properties. This is my belief on the matter. And my belief is supported by doing calculations when you increase the size of those systems and you start losing the coherence, the individual coherence, and you lose all the things that people call quantum. Sometimes you don't, and this is when the two models will be different a little bit, but it's something that you can do. It's updating the observable of the detector that you couple and the internal dynamics of the observable of the detector. It's in the M of T, if you want. Don't think of it as a two-level system or a many-level system. Think of it as a global degree of freedom of the system that couples to the field. That's really fantastic questions, all of them.
If there's no more questions, let's thank our speaker.
Thank you.
We got started late, but